Okay, so we have 3 lectures left. Today, I will first talk about how to generalize the Cartan model to a connected Lie group. Okay? And then in the second lecture, I will talk about some applications of equivariant cohomology, just to show you what equivariant cohomology is good for. And then on Monday, I will do the proof of the equivariant de Rham theorem. Okay? Just 1 hour, and that will be the end of the course. Okay? So, so today G will be a connected Lie group. Acting on the manifold N, and G is the Lie algebra of the Lie group G, okay? And then we choose a basis for the Lie algebra. And it has a dual basis, theta 1 to theta n. And then we can take the exterior algebra of the dual Lie algebra. And we can also take the symmetric algebra of the dual Lie algebra, and there we will write the dual basis as U1 to UN. Okay? And the degree of theta I is 1, because they are 1 forms, but the degree of UI is 2. And then I will use the shorthand. A sub I is A sub I1 to IM. Okay. And theta sub I is theta sub I1 which theta sub IN. Okay. And often I will omit the wedge sign, so I will just write that as theta 1 to theta I1 to theta IM. And then I sub I is I sub xi, L sub I is L sub xi. Okay. So that's the notation. Okay. And the Lie algebra of the Lie algebra is the exterior algebra of the dual tensor with the symmetric algebra of the dual. Okay? And now this is over R. Doing everything over R. And so this, in terms of the basis, it's the free exterior algebra in the thetas tensor with the polynomial algebra in the U's. Okay? Because the U's have degree 2, so they are commutative. And the thetas are anti-commutative. Now this means that an element, okay, and then an algebraic model for EG cross N is, well, this Lie algebra we showed is an algebraic model for EG. Okay. And an algebraic model for M is the de Rham complex. So the tensor product, that's an algebraic model for EG cross M. And an element of this algebraic model, which if you write it out is lambda G dual tensor with SG dual tensor with the Lam complex. So an element in this algebra can be written as A is equal to, okay, the exterior algebra has finitely many basis elements, right? This is finite dimensional. This is not finite dimensional because polynomials can have arbitrary degrees. But here, you can't have arbitrary degrees because if you raise any of these to the second power, it's 0, right? Theta 1 squared is 0, theta 2 squared is 0. So these can only occur to the first degree. And so either they don't occur or they occur just once, or they occur twice. There are two of them, but they're different. I is less than j, okay? And so on. And then the one with the most thetas would be A1 to n, theta 1 wedge theta n. Right? So you can write out the terms in terms of the number of thetas that they have. And then these AIs, they are in here. So they are polynomials in U with coefficients in the forms. They are. Okay. All right. So you can write an arbitrary element of the Weil algebra tensor with the de Rham complex like this. And then such an element is basic if it's horizontal and invariant. So A in WG tensor with omega n is basic if one, it's horizontal, so IXA is 0 for all x in G. Okay. This means it's horizontal. And then 2, LXA is 0 for all x in G. So this means it's G invariant. Okay. So basic means it's horizontal and G invariant. Now this, you don't have to use all the elements of the Lie algebra. Okay. You can just use a basis. So you can just test x1 to xn. Now, so the first thing I want to do is to identify the horizontal elements. Okay? And so there's this theorem. There is an algebra isomorphism between the horizontal elements and, okay? So the claim is that the horizontal elements are precisely the ones that don't have any theta in it. So it's SG dual tensor with omega n. Okay? So there's an algebra isomorphism, and it's given by, you take A and you write it like that, like A0 plus, okay, the sum of terms with theta sub I. You write it like that, okay? Where A sub I is in SG dual tensor with omega n. Okay? And you drop all the terms with theta in it. So you just map it to A0. Okay? I claim that that's an isomorphism. Okay. So I'm going to give the proof for just n equals to 2. Because the general case is similar. But the proof is a little bit simpler when n is equal to 2, okay? So when n is equal to 2, then A is A0 plus A1 theta 1, A2 theta 2. And then you have one more term, A1, 2 theta 1, 2, right? So that's all you have when n is 2, okay? And so we want to know when this is horizontal. So that means we want to apply Ix1 to it. So Ix1 of A should be equal to 0. Now, what's Ix1 of A0? 0, right? Because you recall that Ix of any theta is theta applied to x, and Ix of any u is 0. Okay. So this A0 has only u's in it, therefore Ix of A0 is 0, okay? And then Ix of A1 is 0, but it's an antiderivation. Just a minute, I think, yes, I now realize that this is not a good way to write it, because you see A1, it's a polynomial in U with coefficients in the omegas. Now the U's have degree 2, even degrees, right? So, but the omegas could have even or odd degrees. And so this A1 could have even or odd degree. And since I is an antiderivation, when you move it across A1, then you could have a degree, you could have a sign, or maybe you don't have a sign. So it could be plus or minus. So yeah, so that's not a good way to write A, because if you write it that way, you don't know what the sign is, okay? So I think I actually should write the theta first. Theta 1, A1. Theta 2, A2, theta 1, 2, theta 1, wedge theta 2, A1, 2, okay? So if I write it this way, then I know exactly what the sign should be. Okay, because theta 1 has degree 1, okay? Yeah, So I really should write the thetas before the a's. If I want to calculate IXA, okay? So I get 0, and then IX1 theta 1 is 1, so then I get A1 here. Huh? IXA? IXA 0? Oh, because A0, A0 is the sum of the u's, UI1 to UIM. It's a number of u's times times a form. Oh, maybe it's not 0, times a form. So let's say times omega I, right? And oh. Yeah, so IX yeah, so IXA0 is going to be, yeah, you have these U's, IX omega I. Yeah, that's right. It's not 0 in general, right? Yeah. All right, so, well, okay, so let's see. Maybe we, yeah. So maybe so maybe I need to keep it there. IX A0. Let's see what happens. Yeah. Okay, yeah. And then the next term is theta 1, IX1 A1. So I will write that as I1 A1. Okay? With the minus sign. Yeah, because it's an anti-derivation. And then the next term, Oh, that's right. Yeah. First, I can contract with theta 1. I get 1. So I get A1. Okay. And then I have minus theta 1. Okay. I1, A1. That's right. Okay, good. And then I apply x1 to theta 2. I get 0. And then I have theta 2 minus theta 2, I1, A2. Okay. And then I apply x1 to theta 1, I get 1. So I get theta 2, A12. And then I move across this, I apply to here, I get 0. And then I move across both of them, so I get plus theta 1, theta 2, and then I1, A12. Okay, so that's what I get, right? And then I also have to do Ix2 of A, so it will be Ix2 of A0. Yeah, and then x2 applied to this is 0, and then I get a minus theta 1 I2 A1. Yeah. Right, that's this, right? And then theta 2 applied to this, so I get an A2. And then minus theta 2, I2, A2. Okay? Yeah. And then theta 2 applied to this is 0. So I get a minus theta 2 applied to this is 1. I2. Yeah, I get a minus theta 1 AI2, right? I2 applied to this. And then a plus theta 1, theta 2, I2 of A12. Okay, good. So that's right, yeah? And you set both of them equal to 0. No, actually, now that I think about it, I think, yeah, Ix, yeah, Ix of omega I should be 0. Well, because the omegas are forms on the base, right? So, like if you like if you have a principal bundle, and you have a form on the base, and you pull it up there, and then you apply Ix to it. Then this by definition is pi star of omega applied to x bar, and then you have other things. Right? But pi star, the pullback, is defined to be omega of pi lower star of x bar. And this x bar is a vertical vector, so this is omega of 0. Okay, so it should be 0. Okay. Yeah. Okay. So up here, yeah. So when we define this algebraic model, now we have contraction with theta and with u. So Ix on any theta is theta Ix. Ix on u is 0, but we have to define Ix of any omega to be 0 also. For omega in n. Okay? Because this is a form on the base. And this is upstairs. Yeah. And x, it represents a vertical vector field. The fundamental vector field x is vertical. Okay? Yeah. So on the algebraic model, this is how Ix works. Okay? You have to define Ix to be 0 on the forms on M. Yeah. Yeah, so this is 0. Okay, so Ix of A0 is 0. Yeah. Okay. Yeah. You see, when you are talking about basic elements, you are talking about the total space of a bundle. And here the total space is this. So it's upstairs. Okay. And so the forms on M, they are in a base. To say that it's basic means that it comes from the base. So this omega already comes from the base. Okay. So Ix of anything that comes from the base should be 0. All right? Yeah?
But I think you didn't visualize the basic form.
Pardon?
Is it the basic form? I don't think so. Just
What? Sorry.
I mean, it is a horizontal form, but
Omega is already basic.
yeah, it's on the base.
Yeah, right. Yeah.
And
So Ix of omega has to be 0.
and the underlying x is a zero vector field, and I just want to see that.
Yeah. No, this X bar is a vector field on this. Well, the thing is, actually, EG is not a manifold. So, okay, so in fact, you can't define this X bar except on approximations of EG. But the thing is, no, what we are doing is we're starting with an algebraic object, okay? And we define contraction and the Lie derivative on this. Okay? This is just a definition. And I'm saying that this is the correct definition. And then we want to show that, in fact, it corresponds to, so then we define algebraically what the basic elements are. Okay? So we get something that's completely algebraic, that has no geometric meaning. And then we have to prove the equivariant Durand theorem to say that those algebraic objects that we define algebraically actually correspond to equivariant differential forms that compute equivariant cohomology. Okay? So up here, I mean, I can define contraction and the Lie derivative any way I like, as long as it's an antiderivation. I'm just making a definition, an algebraic definition. Okay? I'm not saying that it has any geometric meaning. So we're going to work it out, and then we find that, in fact, it has a geometric meaning. Okay? So, yeah, right.
Not just acting only on the.
That's right.
So I think you still have action on M that. I mean, I think if you define the output model this way, it doesn't correspond exactly to the geometric situation of the diagonal action. So when you're, I mean, in your, like in this key project for M, this picture of your right this
yeah.
is like you are only considering the action on each G. You have no action on M. But that's not what happened.
That's right, yeah. No, but the thing is, okay, here, if I have something in the base, okay, now this is the pullback up to P.
Exactly, but when you define the X bar, the fundamental vector field
Yeah.
X bar,
Yeah,
fundamental vector field X bar, the definition depends on how your action is defined.
yeah,
And in
right,
this case,
right.
the action of G on P is a diagonal action. It's not just acting on the fiber part. It has
Yeah, well, it doesn't matter what the action is. Pi lower star of X bar is always 0. Hmm?
Did you actually, you say if action on P is non-trivial, it's not the
No, this is the fundamental vector field on P. Okay?
P, right? But
Yeah.
how do you define
It doesn't matter how it
the
acts.
definition depends on action, right? The fundamental vector field,
That's right. Yeah.
you need to look at what your action is to know what the fundamental vector field is.
That's right. Yeah.
So if your action has M direction, then when you project, you can see zero.
No. It doesn't matter. For any action, the fundamental vector field always goes vertically, and so the projection is always 0. It doesn't matter what the action is.
But the fiber is not fine.
Yeah. This is not the fundamental vector field on M. It's the fundamental vector field on P.
That's why
Yeah.
you need to look at
Yeah.
action on
Yeah.
Sorry, I'm confused. Is what is the fiber of that part? Is it
Huh?
is the BG? What's the
Okay.
fiber? Is the
Well, yeah. I mean the fiber will be, well, I mean it's going to be a mix, right, of the two. Mhm.
is it? Do you have to quotient the diagonal?
Yeah, and this is the diagonal action. Yeah, but I'm saying that it doesn't matter what the action is. For any action, you can define a associated fundamental vector field, and that fundamental vector field always has this property: the pi lower star is 0 for any action. It doesn't matter what.
So what? But does the proof actually acts on a fiber?
Yeah.
But it wouldn't be the case if the fiber is BG.
No, the fiber, this is a principal bundle, so the fiber is always isomorphic to the V. It's always isomorphic to G. Yeah, the fiber is always G, no matter what the action is. Yeah. Okay. But in any case, I mean, this is just a motivation, okay? So I mean, I can define the contraction any way I like on this algebraic object, and that's how I'm going to define it. This is the definition of the contraction. Okay? So we're going to work with that definition and then work out what the basic elements are. Okay?
Well, one thing is, I mean, when you are talking about
Yeah.
the homotopy quotient, you
Yeah.
are not looking at P as a bundle, as a five bundle over M. You are looking at P as a five bundle over P mod out by G by the diagonal action, right? So actually it should be a five bundle over BG, not M. When you are talking about homotopy quotient. I agree P is a five bundle over M, but I'm saying when you are talking about the homotopy quotient, you are not looking at the M, you're looking at five bundle over BG, because you are talking about action.
All right, yeah. Yes, I think you have a point there, but yeah, okay, but yeah, but okay, so maybe my motivation isn't good. Let me see. No. So, yeah, this is MG. Yeah. P. Yeah. No. This is. For our. Yeah. Right. This is. So our P is this, right? And then with the diagonal action, the base is mg. Okay, so maybe this is not the right motivation. No. Right.
But my question is, I just don't see why this definition kind of corresponds with geometry.
No. Well, let me see. Yeah. All right. So I'm going to make this definition, okay, because it gives me the correct Cartan model that will eventually give us equivariant cohomology. So I think maybe when we go through the proof, we'll see why it has to be defined this way. But yeah.
To prove this theorem, it doesn't need less than d0.
Pardon?
I can prove it by necessary less condition.
Oh, just leave this alone? Okay. You just. Oh, I don't. Just leave it like that? Oh, okay, yeah. Okay, so let's do it that way. Let's not define it to be 0. Okay? So, okay, yeah. So let's just write out what this condition says, yeah? Now. Oh, of course. Yeah. You're right. Yeah, I think you're right. So yeah. So like this is these two terms don't have theta in it. Yeah. So there is a condition there. Yeah. All right. Yeah. Yeah. All right. So I forget everything I said there. I think you're right. I think you're absolutely right. We don't define it to be 0. Okay. Don't define I, and then here, then we have this term and this term, and so that's right. So what we get is that the sum has to be 0. The sum has to be 0. So A1, so we see that A is basic if and only if A1 is minus I1 A0. Right, that's, sorry, A is horizontal. That's one condition. Okay, and let's look at the terms with theta 1. So this has to be 0, I1 A1. Okay, but A1 is minus A1 0, so automatically this will imply that I1 A1 is I1 A0 is 0. Okay. Yeah, so this will be 0. And then the terms with A2 is, there are two of them, so A1, 2 has to be I1 A2. And then this term, so I1 or A1, 2 has to be 0, but this implies that I1 or A1, 2 is I1, A2, so that's 0. Okay, so you get these two conditions, and then here you have A2 has to be, and this have to sum to 0. So A2 has to be minus I2 A0. A2. Yeah. And that will imply, just a minute, and then this term, the one with theta 1, so there are two of them. So A1, 2 has to be minus I2 A1. A1, 2. A1, 2. Minus I2 A1. Now, let's see. That takes care of this and this. And then this has to be 0. I2, A2 is 0. But that implies that I2, A2. Okay, so that's this one. Okay, and then this one, I2, A1, 2 has to be 0. But this implies that I2, A1, 2 is this. Okay, so we have these four conditions. Oh yeah, yeah. That's right. Because A2 is this, so this is minus I1, I2, A0. And this one is A1 is that, so this is I2, I1, A0. So these two conditions are the same. Yeah, so you can drop one of them. So this one is redundant. and therefore we can drop it. Okay? And yeah, so there are really three conditions. There are really three conditions. So A1 is minus I1 A0, A2 is minus I2 A0, A12 is I2 I1 A0. Okay? So everything can be written in terms of A0, and that means A is equal to A0 minus I1 A0 minus I2 A0 times theta, minus theta 1 minus theta 2, and then plus theta 1 theta 2 I2 I1 A0. Okay. And you can write this as, now I can move this here. If I move it across two things, the sign doesn't change. Okay. And so I can factor this. This is 1 minus theta 1 I1 A0 minus theta 2 I2 1 minus theta 1 I1 A0. And so this becomes 1 minus theta 1 I1 1 minus theta 2 I2 A0. Okay? This is for n equals 2. You see that if n equals an arbitrary positive integer, you just have n of these. Okay? And what this says is that, okay, now I have a map by dropping all the terms with theta, and now I have an inverse map. Starting with A0, I can define A by just multiplying by these two operators. Okay? So, all right. So if I call this phi, then phi has an inverse. Okay, that takes A0 to 1 minus theta 1 I1, 1 minus theta 2 I2 of A0. And therefore, it's an isomorphism. Okay? And it's an algebra isomorphism because when you add two of these things, this is the constant term. Without theta, they add. Okay? And if you multiply two of the things, the constants multiply. Yeah. So phi is an algebra homomorphism, and therefore an algebra isomorphism. Okay? And then, now that's just the horizontal element, and the basic elements it's the horizontal elements that are also invariant. So it will be this. Now, the horizontal elements that are invariant under G. Okay? And G acts on both of these because it's a diagonal action. So hence, So you have this isomorphism. And this is called the Weil model for equivariant cohomology. And this is the Cartan model. It's the Cartan model. And so the equivariant Durand theorem says that either of them will compute equivariant cohomology. Okay? Now, we already have a differential here on the Weil model because we know how D acts on the Weil algebra and on the Durand complex. Okay? So we have to find what does that differential correspond to? You know, it will be given by some other formula on the Cartan model. And once you have the differential, then you can compute cohomology. Okay? And then you get the equivariant Durand theorem. So, yeah, so maybe in the next hour we'll try to work out the differential. But I also want to show you the applications. Yeah. And today, yeah, I'm glad that you actually pointed out that Ix on the forms is not 0. Yeah, you're right. Yeah. So, yeah. So, yeah. That's right. Okay. So I think everything works out. So, so we'll take a break for 10 minutes, and then we'll come back. Okay.